Hi students, welcome to this session, and in this session I am taking how to calculate equilibrium constant values in different situations with some multiple choice questions. So at first I taken the law of chemical equilibrium, and after taking that we can take few MCQ based on calculation of equilibrium constants. So let us start with the law of chemical equilibrium. All of you know, right, how to write the expression for equilibrium constant. So we can take symbol equilibrium constant as Kc. At first I have taken an equation here. A moles of A reacts with B moles of B to form C moles of C and D moles of D. Okay, A moles of A and B moles of B, this is actually in equilibrium with C moles of C and D moles of D. So we can take here the small letters, what's mentioned here, right? A, B, C, small c and small d. These indicates stoichiometric coefficients, right? So that many moles of reactants and products. So that we can take it as stoichiometric coefficients. And if we take this equilibrium now, we can easily write the rate of two reactions, right? As you can see, we got forward reaction and we got backward reaction. Okay, so rate of forward reaction, we can easily write the expression for that by using a law called law of mass action. So what it says, law of mass action, rate of any reaction is directly proportional to the active or can take concentration of reactants, right? So if we take a rate of forward reaction here, RF is proportional to for forward reaction we got these two, right? A and B as a reactants. So what we can write now, RF is proportional to A to the power A and B to the power B. But remember, if we take a rate of forward reaction directly proportional to the concentration of reactants, we need to add one more sentence, right? Concentrations of reactants raised to the power, we can take these powers nothing but their stoichiometric coefficients, right? Stoichiometric coefficient for A is, you can take small a, right? And for B we got small b. Okay, this is according to law of mass action. Now if we remove this proportionality sign, we can take equal sign by taking one constant, and we can call this constant as a rate constant, and particularly for the forward reaction, so we can take it as a rate constant for the forward reaction. So we can take symbol as Kf. So we got expression Rf is equal to Kf into concentration of A to the power A and B to the power B. Similarly, we can apply for the backward reaction also. So if you apply law of mass action to the backward reaction, now if you see the backward reaction, we will be having these C and D will be taken as reactants, right, for the backward reaction. So we can take expression now. You can see here Rb proportional to concentration of C to the power C, D to the power D. And if you remove that proportionality sign, we get expression as Rb is equal to Kb into concentration of C to the power C and D to the power D. So what we got now, the two expressions, right? One is Rf and Rb, rate of forward reaction and rate of backward reaction. So once you get that, now we can take at equilibrium. At equilibrium, the condition is what? A rate of forward reaction is equal to rate of backward reaction. So this condition you can take, right? Rate of forward reaction equals to rate of backward reaction, and we already got, right, Rf and Rb expressions. So Rf is nothing but Kf into concentration of A to the power A and B to the power B, whereas Rb is equal to Kb into concentration of C to the power C into D to the power D. Okay, so now just rearrange the terms now. Take this Kb to the LHS part, and these two terms you can take to the RHS part. So upon rearrangement, what you get now? Kf by Kb is equal to C to the power C, D to the power D, divided by A to the power A and B to the power B. So we got expression for Kf by Kb, and Kf by Kb we call it as Kc, nothing but equilibrium constant. So what we can write now, the meaning of equilibrium constant, it can be defined as, we can take like the ratio of a rate constant of forward reaction to the rate constant of backward reaction. So we can remember this is very important, right, in terms of concentration. So Kc can be written as C to the power C into concentration of D to the power D divided by concentration of A to the power A into concentration of B to the power B. Right, so this is the expression for equilibrium constant. Okay, right, now we can take law of chemical equilibrium, okay, which says or can take is nothing but the definition of equilibrium constant. Right, you can see in equilibrium constant we got numerator, C and D are products, right? In the case of forward reaction, A and B are reactants, right? So you can see here the statement, at a given temperature the product of concentrations of reaction products. Okay, first what you taken here, we got products, right, in the numerator. So it is nothing but product of concentrations of the reaction products raised to the respective stoichiometric coefficients. Okay, this is important. You can see here we got small c and small d, right? So that indicates the stoichiometric coefficients. Okay, coefficient in a balanced chemical equation divided by, that's the ratio right now, so divided by the product of concentrations of the reactants raised to their individual stoichiometric coefficients has a constant value. Okay, so the constant value we can take it as equilibrium constant, symbol is Kc. Right, so this we can take it as a law of chemical equilibrium. Okay, right, so once you learn this, the next one, we got few equations to be taken, or how to guess equilibrium constant for few reactions. Okay, you can see here, first one I taken general reaction there, A moles of A, B moles of B giving C moles of C and D moles of D. If we take equilibrium constant for this reaction as Kc, now what I do, just reverse the reaction now. C moles of C plus D moles of D giving A moles of A and B moles of B. Okay, if we're having a reverse reaction, we can easily get the value of equilibrium constant. That's a new equilibrium constant, right, for this reaction. So K dash C I have taken, right? So K dash C is equal to, it should be the reciprocal of the equilibrium constant for the reverse reaction. Okay, so these two are reverse reaction, right? So if it is Kc for the first reaction, then we should take 1 by Kc. Okay, we got many questions asked based on this, based on like reverse reactions. Okay, they will just reverse the reaction and they may ask what is the equilibrium constant value. So K dash C is equal to 1 by Kc. Now the third reaction, you can see it's almost similar to the first one, right? Only change is multiplied by some number here. So I taken n. So if you multiply by certain number, you can see the difference, right? In the first you can see Kc, and here K double dash C is equal to Kc to the power n. So whatever number is multiplied here, it should be raised to the power or can take Kc to the okay, should be raised to that power, okay, n. Okay, so in this way we can easily find the equilibrium constant values, okay, for certain cases. Okay, now we can take few problems based on calculation of equilibrium constant. I have taken 5 questions here, so we can take first one now. As you can see, the first one, let me read that. At a certain temperature, 1 mole of PCl3 and 2 mole of Cl2, okay, so we got two reactants, right? One is PCl3, other is Cl2, were placed in a 3 liter container. So volume is given as 3 liter. Okay, when equilibrium is reached, only 0.7 mole of PCl3 is remained unreacted. Okay, so unreacted PCl3 is how much? 0.7. okay, right. Calculate the value of Kc for the reaction. So at first in calculating equilibrium constant, So the first step is what? We need to write the equation. So the equation given is here PCl3 reaction with Cl2 giving PCl5, all in gaseous state. Okay, now the next step is what? We need to mention the initial moles. Okay, we can even write one more as a stoichiometric coefficients, right? PCl3 1 mole react with 1 mole of Cl2 giving 1 mole of PCl5. So it's actually 1:1:1 ratio, right? Okay, now the next step is initial moles. You can see initial moles, right? First here you can see 1 mole of PCl3 is given, right? So I have taken 1 mole here. Then chlorine, how much here? 2 moles is given in the problem, so I have taken 2 moles of chlorine. Initially there is no reaction, right? Or reaction has not yet started, so there is no PCl5 formation. Okay, so this should be taken as 0. Okay, initial moles we got. Now at equilibrium, what are the number of moles of these 3 components? Okay, PCl3, Cl2 and PCl5. Okay, just see now, one more data is given here. 0.7 mole. Okay, this value remains unreacted. This is at equilibrium. Okay, so the concentration of PCl3 at equilibrium is 0.7. Now if we take 0.7 remaining, right, then how much should react with Cl2 there? You can see initially 1 we got and 0.7 is unreacted. Okay, so how much should be reacting now? We can take this, right? To get 0.7 we should subtract 0.3 from 1, right? So 0.7 equal to 1 minus 0.3. So it means 0.3 moles of PCl3 is reacting, right? Okay, now 0.3 moles is reacting means we can easily write for even Cl2 also, right? Now Cl2 is having 2 moles initial, right? Initial moles is 2 and only 0.3. Okay, as I said already here, the ratio is 1:1:1, right? So if you take 1 mole of PCl3 will react only with 1 mole of Cl2. Okay, so what you can write now, if this is 0.3 reacting, so here also we should take 0.3, right? So what happens now? Initially 2, so 2 minus 0.3 means it is 1.7. So chlorine at equilibrium, how much it is present now? The moles of chlorine is 1.7. Now again see the ratio here, stoichiometric coefficients. 1 mole of PCl3, 1 mole of Cl2 gives 1 mole of PCl5, right? So what happens now? 0.3 is reacting PCl3 with 0.3 mole of Cl2. It should give 0.3 mole of PCl5 also. So what's the conclusion now? Or at equilibrium the moles are, 1 is 0.7, that's PCl3, then Cl2 is 1.7 and PCl5 is 0.3. So now we can use these equilibrium concentrations, moles, to find concentration. Number of moles we know, and we know even the volume also, right? The container is 3 liter, so we can easily find the concentration. The concentration can be taken as number of moles by volume, particularly molarity. So number of moles is 0.7 for PCl3, 0.7 by 3, this is first one. Second one is 1.7 by 3, that's for chlorine, and for PCl5 it is 0.3 by 3. Right, so we got concentrations, right, at equilibrium. So now we can write the expression. We already know how to write the expression for equilibrium constant. So Kc is given by concentration of product. PCl5 is product, right? The stoichiometric coefficient is 1 here, so you can take it as directly 1. Then PCl3 reactants we got 2, right? Concentration of PCl3 and concentration of Cl2. Just substitute the value, we'll get the answer. PCl5, how much you got concentration? PCl5 is 0.3 by 3, right? Then this is the concentration of PCl3 and this is the concentration of Cl2. Okay, so if you simplify, you'll get answer as 0.76. So the right answer for this question is 0.76. You can see the option is A. Right, so this is the first question based on calculation of equilibrium constant. Let's go for second question now. Okay, second question is, at a certain temperature 50% of HI is dissociated into we can take products here H2 and I2. So we need to find again equilibrium constant here. Right, just see the data given. Only they said 50% of HI. Right, I said okay, the rule, right? First we need to write equation, balanced equation. So 2HI in equilibrium with H2 and I2. You can see the stoichiometric coefficients I taken. 2 moles of HI will dissociate to form 1 mole of H2 and 1 mole of I2. Right, now just see initial what I taken now. Initial, it's not given anything here, right? So I had taken it as 2x moles of HI, or I can take like the concentration to be taken as 2x. Okay, as initial there is no dissociation of HI. The concentration of H2 and I2 to be taken as 0 and 0. So what I had taken now, initially I assumed okay the concentration of HI as 2x. Right, now just see what they say here in the question. 50% of HI is dissociated. Okay, so if you take 50% of this 2x, how much it will be? X, right? So this is 50%, right? Okay, if you remove that, then unreacted HI or undissociated HI will be x the concentration, right? So 2x minus x equal to x. So what you got now? X is the concentration of HI at equilibrium. Okay, right, now at equilibrium what are the concentrations of H2 and I2? So how to find that now? You know how much reacting here? So x moles, right, reacting. Okay, so if you take x moles reacting, or they said 50% of HI dissociated. Okay, only x moles is dissociating. Okay, so you can see now 2 moles of HI will give 1 mole of each. Okay, now if you take x moles dissociating, so it should be made half right now, because 2 moles gives 1 mole each, then x moles should give x by 2 and x by 2 moles of H2 and I2. So we got number of moles or concentration of hydrogen and iodine. So once you get all the concentrations at equilibrium, we can use the expression again, right? Similar. Kc is equal to the products are H2 and I2, right? Concentration of H2 and concentration of I2 divided by concentration of HI to the power 2, because we got stoichiometric coefficient here as 2, right? Okay, so once you write that, just substitute now. H2 concentration is x by 2, I2 concentration is x by 2, and HI concentration is x to the power 2 it is, so x square, and if you simplify you'll get 1 by 4, that's nothing but 0.25. so the right answer for this question is 0.25. Okay, let's go to third question now. Okay, third question is a reaction between iodide ion and iodine molecule to form I3 minus. Right, so I minus and I2 are in equilibrium with I3 minus. Right, let me read the question. Okay, this reaction is set up in aqueous medium. We start with 1 mole. Okay, first data given is 1 mole of I2. So I2 concentration is given. Okay, sorry, moles is given, 1 mole. Then 0.5 mole of I minus in 1 liter flask. So volume is given, right? And 0.5 mole of I minus. So we know number of moles of iodine as well as iodide, and even volume given. Okay, that is that's given as 1 liter. Now after equilibrium, the excess AgNO3 gave 0.25 mole of yellow precipitate. Then the equilibrium constant is, right, so just see here, first we need to get the idea about this. They're adding AgNO3. Now if you add AgNO3 to this equilibrium, what happens then? You know, this iodide will react with AgNO3, right? And if it reacts with AgNO3, it forms AgI, and AgI is having yellow color, right? So you'll get yellow precipitate of AgI. Okay, so what just said, 0.25 moles of yellow PPT forms means that should be depending on, or it affects to the concentration of iodide ion. Okay, right, now let us see its the solution part. So first we have taken equilibrium there, again I minus plus I2 giving I3 minus. Okay, now the initial at first is also given right there. We're having 0.5 mole of I minus, 1 mole of I2 gives, sorry, this is initial, right? There is no formation of I3 minus, so it will be taken as 0. Okay, now just see how much PPT they said, how many moles? 0.25 moles of yellow PPT forms. Right, now if we take 0.25 mole of yellow precipitate, nothing but what? 0.25 mole of I minus combining with AgNO3. You know the ratio is what? If we take AgI, the ratio of I minus and Ag plus should be 1:1, right? So we can take what? If it is 0.25 mole of yellow PPT, that's AgI, nothing but 0.25 mole of I minus. Okay, right, now if we take 0.25 mole of I minus is combining with silver nitrate, it means how much remaining now? That should be in equilibrium, right? Okay, just see now at equilibrium what we take. Okay, what you can write now at equilibrium? 0.25 minus 0.25, 0.5 minus 0.25. Okay, from where you got this one? Why we need to subtract? Because 0.25 mole of I minus is combining with AgNO3 to form yellow PPT of AgI. Okay, so that's the reason why we need to subtract. Okay, right, so how much will get answer here? As 0.25. Next one, so if 0.25 is only reacting, okay, now just see the stoichiometric coefficients here, right? 1 mole of I minus, 1 mole of I2 will give 1 mole of I3 minus. Okay, so it means if we take 1 mole of I minus, it reacts only with 1 mole of I2, right, to form 1 mole of I3 minus. So what you can write, if in this case 0.25 moles of I minus is remain organic reacting, so it means what? It should be 0.25 moles of I2 also, right, and 0.25 moles of I3 minus will form. Okay, right, just see now in this case 0.25 remaining for iodide, then I2 will be 0.75 remaining, right, because 0.25 is reacting with that. Okay, if 0.25 is reacting, what you can write, remaining will be 1 minus 0.25, it is 0.75. And if 0.25 iodine iodide reacting, it should form 0.25 moles of I3 minus. Okay, so we got equilibrium concentrations now. Then you can write the expression. Okay, Kc is equal to I3 minus divided by I minus concentration into concentration of I2. So if you substitute the values there, 0.25 by 0.25 into 0.75, and if you simplify, you will get answer as 1.33. So you can see here the right answer is option A, 1.33. Right, so that's about third question. Let's take next one now, fourth one. Okay, in fourth, let me read first again. In a reaction A plus B giving C plus D in equilibrium, right? A, B are in equilibrium with C and D. The initial concentration of A and B were 0.9 mole per dm cube each. Okay, the concentration of A and B is same, right? Initial concentration that's taken as 0.9. At equilibrium, the concentration of D was found to be 0.6 mole per dm cube. Okay, equilibrium concentration of D is given, right? You know, D is one of the product. Okay, now what is the value of equilibrium constant? So we need to find again the value of Kc. Right, so again first we can take equation A plus B in equilibrium with C and D. Stoichiometric coefficients I have taken, right? 1, you know, all 1, right? 1:1:1:1, right? Okay, initial concentrations given here A and B. A is 0.9 and even B is also 0.9. As no reaction is started, so we need to take number of moles, so the concentration of products as 0. Right, now at equilibrium what happens? One data is given here, right? You can use this now. 0.6 mole per dm cube. D concentration is given. Okay, so at equilibrium concentration of D is given as 0.6. right. Now if it is given as 0.6, what about C concentration? Okay, concentration of C should also be same, right? 0.6 only, because the ratio is 1:1 here. So if D concentration is 0.6 at equilibrium, C should also be 0.6. Okay, right. Now just see products C and D, we are getting 0.6 each. Okay, now so if you guess regarding reactants now, okay, so it has to be what? 1:1:1:1 I said, right? Stoichiometric coefficient. So it means 0.6 mole organic concentration of C and D is 0.6. It means A and B should also be 0.6, right? Okay, so just see here how much part is reacting. In A, 0.6 moles is reacting, right? And in B also 0.6 moles is reacting. But we need to write what is remaining, okay, the concentration of A and B at equilibrium. So what we need to take now? 0.9 initial minus reacting is how much? 0.6. So remaining is 0.3. The same applies to even B also. Okay, so it is 0.3. And C and D we are having is 0.6 and 0.6. So be careful here. Most of the time what happens, the students will take like 0.6 here, 0.6, and again they'll take here also A and B also as 0.6 only, but only it is reacting part. Okay, so 0.6 if it reacts, then we need to subtract from the initial concentration. Okay, so remaining will be what? 0.3. okay, now it is simple. Kc is concentration of C, concentration of D divided by concentration of A into B. Just substitute the values now. 0.6 into 0.6 divided by 0.3 into 0.3, and if you simplify you'll get answer as 4. So the right answer for this question is option B, that is 4. Right, next one. Okay, last question is 2 moles of N2 is mixed with 6 moles of H2. Right, number of moles of N2, we got 2 moles and 6 moles of H2 in a closed vessel of 1 liter capacity. Volume is given. If 50% N2 is converted into NH3, okay, so only 50% is getting converted into ammonia at equilibrium. The value of Kc, right? So equation is given here. The Haber's process. This is based on that, right? N2 plus 3H2 giving 2NH3. Okay, I take an equation here. N2 plus 3H2 giving 2NH3. Stoichiometric coefficients are 1 mole of N2 react with 3 moles of H2 giving 2 moles of NH3 ammonia. Okay, now initial concentration is given. Initial concentration of N2 is 2 moles, hydrogen is 6 moles, and as you know, no reaction started, so we need to take product concentration as 0, or you can take number of moles, right? It's not concentration given, number of moles. Now at equilibrium, the number of moles, just see the again the data here. 50% of N2 is converted into ammonia. 50% is converted. Okay, so initial 2 moles, right? So if you take 50% of this, you can see, right, 2 minus 50% of 2, right? So if you take this, 50% of 2 means it becomes 1, then 2 minus 1, it is, you got 1 mole. Okay, so only 1 mole of N2 is reacting. Okay, now just see about hydrogen here. So if we take 1 mole, just see the ratio now. In this case we got 1 mole of N2, then 3 moles of H2, right? 3 moles of H2 gives 2 moles of ammonia. Right, now just see So this is clear, right? Now 2 minus 50% of 2, that is 1. So 2 minus 1, you can take it as 1 mole. Okay, now here 6 is initial moles given, right? Minus, okay, again if you take 50% of that 6, it becomes 3, right? And if you take, it becomes 6 minus 3, it is 3. So what you got now? 1 mole of N2 and 3 moles of H2 at equilibrium. Okay, now how many moles of ammonia will get? So you can make use of stoichiometric coefficients. Now it's 1 mole, 3 mole forms 2 moles of ammonia. So it's the same, right? Here also you got 1 mole, 3 mole, and it should form 2 moles of ammonia. Okay, so what we get then, we can take the expression again, Kc NH3 to the power 2, stoichiometric coefficient is 2 here, right? So NH3 concentration to the power 2 divided by concentration of N2 into concentration of H2 to the power 3. Okay, just simplify, substitute and simplify now. 2 to the power 2 divided by 1, that's the N2 concentration, into 3 to the power 3. Okay, H2 is taken as 3, right? 3 moles. Or you can take even. Okay, this is moles, but remember here is given 1 liter capacity, right? So if we take number of moles by volume, we'll get the same, right? So in this problem, number of moles is nothing but its concentration. Okay, so I'm taking directly 3 to the power 3. So if you simplify, you'll get answer is 4 by 27. So the right answer for this question is option A, 4 by 27. Right, so that completes this session. Okay, so if you want me to add some more questions or any other bits, okay, you want me to explain, you can comment. And if you like the video, please subscribe to my channel. Thank you.